always want several people, possibly with different strengths and different expertise behind them, to provide you with their best estimate. And then by combining it all, you can actually make usually a much better decision. And that's exactly what's happening whenever we're doing some data science, whenever we're looking for the best prediction from our models. So ensemble modeling aims at forecasting a given target variable with whatever highest accuracy, best AUC, right? You already know a bunch of metrics, lowest mean squared error, you make a pick, by actually combining the prediction of several models. Now, ideally, you want these models to be kind of playing on different strengths, right? So you might want one person working for a company, somebody maybe less biased, that has more experience on the market, then maybe somebody that knows the technological outlook for the whole industry, and etc. They have different perspectives, they might provide you with different opinions, but actually by combining it all together, you might end up with a much more accurate prediction. So this is pretty much what we kind of ended up doing here. It's like asking a bunch of experts, and then you can put all together their estimates. Now for us, when we're actually talking, when we're going back to the data science, this sort of combination, this concoction, solves a whole bunch of issues for us that you might familiarize yourself during the past lectures, like Biasvariance tradeoff, strength diversity trade-offs, and little something that's called Ensemble Margin. We're going to be talking about it. It actually can solve a whole bunch of inherent problems that comes whenever you're picking up for just one model, just one predictor, right? There is no free lunch. They all have strengths and weaknesses. You always want to make sure that you're accounted for all the pitfalls. The empirical evidence shows that these sort of combinations are super strong. Now, what we're going to be talking about today is the whole idea of ensemble learning. I'm going to introduce you to some kind of starting ways of getting it to work. We're going to talk about the bagging algorithm. We're going to get introduced to the random forest, which is definitely one of the, up to today, even though it's fairly old, the random forest algorithm, which is still one of the strongest on the market and one of the very, very widely accepted ones when it comes to the actual models in deployment with the startups, with the bigger companies that actually have their product running with the general public. And then we're going to talk a little bit about ensemble learning theory. Now, I'm going to make a little detour somewhere in the middle of, in between bagging algorithm and random forest. I would like to talk to you more about the whole Biasvariance trade-off. Hopefully it's not entirely a new thing for you. I feel that this is one of the toughest bits that is kind of overlooked, and then this gap in understanding is going to follow you, or hopefully not after today, throughout the rest of the courses, and actually somehow it keeps on coming back and haunting students, causing bunches and bunches of mistakes, even when it comes to, you know, whatever state-of-the-art deep learning models you might be dealing with next semester at Adams. This is in the longer term. In the shorter term, those of you who are working on the competition, ensemble models are extremely potent to give you very, very nice performance. So in case nothing works so far, I think ensembles models should propel you very nicely forward in the performance of your models for the competition at least. We will actually also go through the technical implementation. Professor Lessman included some code bits so that you have a good understanding how exactly it's going to be looking like in the R code. It's going to be, I think, the topic of the next tutorial, so not this one today. However, we'll go through the steps so that you have a pretty firm understanding how exactly the whole ensembling is happening when it comes to the data science application. So let's start with the bagging algorithm. So today is the first part of the whole ensemble learning lectures. There are a whole bunch of algorithms that can be used in ensemble learning. We're going to cover two, and more will be to come during the next lecture next week. So the bagging algorithm is going to look very similar to the following situation, which is kind of classic. I think it's like in all the educational books. So in case I have a big jelly bean jar here standing on my table and I start asking all of you, how many jelly beans do you think there are? You're probably going to give me some numbers, and then I can average that, and then probably we're going to end up with a fairly good number. What is the difference between this and what we just performed in the beginning? You all will be at exactly the same level. Unless there are some professional jelly bean predictors here, you're probably going to have like give and take same or similar estimates across. So there's nothing about the expertise that's going to kick in. You all are at the same level, which basically makes it a homogeneous ensemble, right? So you have same predictors, same opinions coming from the same background. However, there are, of course, tricks to make it work nicely. So initially, bagging is coming from the Bootstrap aggregation naming, introduced by the guy that's been hottest on the market for many, many years, who is Leo Breiman. He's also going to be the one who is giving us the random forest algorithm. So homogeneous ensemble strategy is when you basically have same predictors, as mentioned. So for example, you have bunches of linear regression or logits that are going to be giving you predictions. So just imagine you're running the same code for 10 times, and you're seeing what exactly is the output of every model. However, there will be a little catch here. We actually want to make sure that these models are not giving you exact same prediction, right? So what we could have potentially run into when we had our stock trading case, if everybody would say, okay, just going up, actually we would run into the problem of maybe, you know, everybody's biased and we're not getting some sort of an opinion that might be, you know, tilting us downwards. So you want to make sure that all of your predictors are at least somehow different, because they need to be maybe grasping different bits of your data. How exactly it works? It's solved by the concept called Bootstrap Sampling. What does it mean? You have a certain original data, right? We have a certain number of observations. If you think about our home credit data, that is a perfect example. You have different observations in this big data set. So what we would like to do is we actually want to take a sample out of it, sample with the replacement, meaning that you might have same observation seen like a couple of times in your Bootstrap sample, right? So you're taking a ball out of the big jar, and then you're giving me a number, and then you pull the ball back. There is a low, but still a probability that you're going to pull out the same ball next time, although most likely it's going to be a different one. And thus, by this random sampling, random pooling, we're going to build our Bootstrap sample. This sample is then going to go into our logit model, and it's going to produce a result for us. And then we're going to perform the very same operation again. We're going to say, okay, scrap that. We have our results, setting aside. Then again, let's start pulling the balls out. We're going to get a different sample. And then we're building a new model, another logit, that's going to give us a certain output, right? A certain number of probabilities. And then, for example, we're going to have a third sample. The number of samples is going to be one of many decisions that you have to make as a data scientist. Usually, the more the better. Of course, depends on the size of your data. Whenever you have millions of observations, you can obviously play very nicely and play a lot with them. Number of those little Bootstrap samples that you have. Now, the number of observations in every sample is another choice that you might be making. Make it too few, and your logit will probably not be able to give you anything meaningless back, right? It's very, very hard to learn from like 3 observations in total. Make it too many, and then there will be very little difference between the original set and the Bootstrap sample, so the whole procedure kind of loses its point, why exactly we're going to see. The good part about this Bootstrap sampling is whatever is not sampled, the stuff that is remaining in our jar after we're done picking for our next sample, can be used to test our results, right? You're already familiar with the train test splitting, that we're training on one bit of the data, and then we're withholding another bit to see how good our model is, right? Because the fact that the model learned to classify perfectly the set that it's trained on doesn't mean anything, right? It's actually a big problem if it learned to predict that set exactly, And this again brings us back to the Biasvariance trade-off. We're going to explore it a little bit more. The bootstrap sampling allows you to have different out-of-bag examples, right? So this is the stuff that basically was not included in your training sample for the testing. So every time you're going to have a different test set in order to check how good your logit was trained, which is very nice. I'm not entirely sure where the 37% number is coming from, but I guess it was somehow calculated in the sense of you will always have different numbers that you will be checking on. What does it mean for us? Imagine there are actually, out of your, 100 observations, 100,000, you have particularly nasty 10,000. These are the people whose behavior is kind of irrational. It's very, very hard to capture, as in our case, if they're going to be good loan takers or not. Just so much controversy going there. In case all of them happen to be in your training set, probably your model can learn, but then it's a big question if it will be able to predict one properly in the test set. So what you might end up having is sometimes you have all of them in the train set and none on the test set. Sometimes you want to have none of them in the train set and all of them in the train set and all of them in the test set. Sometimes you want them to be distributed. This way, all those different logits you're training are basically going to be differently strong in being able to capture those complicated cases. This way, when you average them all together, you can get yourself a fairly strong and fairly robust predictor that you can make sure picks up on those complicated cases. So again, given the sample 1, we would have a bag of out-of-bag examples 3, 4, 6, 9. You can see they're not included in the original one, and so on and so forth. Right? We have different out-of-bag examples. We can this way make sure that all of them, that we can test the prediction of all the models on the different examples. Now, the tough thing about this, and why exactly I would imagine the previous lecture and maybe today's lecture seems kind of less exciting than when we're exploring super potent algorithms that give us super nice accuracies. All this stuff kind of seems to be, yeah, but my first problem is to get my model to work. Why do I need to bother about, these different test sets? Unfortunately, this is exactly what makes machine learning such a dubious topic for the industry, right? Because people coming as a data scientist and working for the industry very often only know how to build the models that's going to produce the best accuracy for you. However, whenever you release this whale into the ocean, whenever your model is actually out there in the wild getting entirely new inputs about your actual consumers, they fail miserably. And then the company has to, deal with a lot of losses and go back and figure out what exactly went wrong. So definitely the AUCs are kind of a sexier topic, like when you have very good models, but making sure that your models are robust and can pick up on all the quirkiest cases in your data is actually of much higher importance when it comes to the true world and the implementation. So it might not necessarily be your biggest concern when it comes to, for example, competition, but the whole idea of overfitting and robustness and stability of models, I would not be surprised if it's extensively represented in the exam, although I don't know. But it's definitely of much higher importance than super cool AUC or super cool accuracy that your models might yield you. So you would not, I guess, expect that much of a difference on the test set, right? So we trained our model, we loaded in our test set, we're looking, okay, what's the accuracy in my test set? Let's say all our sample 1, sample 2, sample 3, we have accuracy of, 98%. Awesome. There is a very high chance that the accuracies on out-of-the-bag examples, right, on our test set is going to be very, very different. As an example of logits and then the trees. So exact same procedure, right? The sampling, prediction, and then test evaluation has been performed on bunches of logits and then on bunches of trees. What you see here is actually the distribution of a classification error. And you can see that it can vary big time. So yes, majority of your models will be giving you a classification error of 0.33, but then some of them are going to have much higher error. So in case you only did it once, for example, and you got unlucky with your bootstrap, you might discard this model entirely because it doesn't give you good performance. Or for example, you got very lucky and you ended up with this little dot at the very bottom above the logit, and you're like, oh my God, this model is amazing, deployed. And then, things crash and burn because you got just lucky on your out of sample. There were no complex cases in your test set, and this performance that you were so happy about doesn't mean anything in the sense of robustness, right? It's not a performance you can repeat on an everyday basis, and this is what we want if we actually want to keep on using the model for some sort of a practical application. You can see that, for example, tree, these are the air part models that you've tried, I think, last tutorial. You can see that they, in general, perform a little bit better, a little bit worse. So their mean error is around 38, I guess. However, again, they're fairly stretched in their distribution, right? So there is no unanimous performance among the trees either. So you want to make sure that you captured all the worst, all the best cases, and then you can say, okay, on average, my models are somewhere on that level, and then you can compare them properly. Because imagine if you built one logit and one tree, and you happen to have the super good logit, and or for example, super good tree, which is 0.28, right, the bottom there. And then you just got very unlucky with the logit, and you got an error of 0.45. And then you compare with them, and then you made a decision, well, obviously, my tree is much better, moving on that direction. You're taking a wrong path, right? Probably, if you experimented it with a little bit more, if you took another sample from your data, you would see that logit on average is actually performing much better. So you need to be very cautious there. This is what bagging potentially can be solving for us, right? The algorithm performs all these steps for us. We can actually see how it's going to work. Now, what exactly is happening after you got your logit outputs or your tree outputs, right? Let's say we're interested in probabilities, so that it will be the bottom variant. And let's say we're just looking at one particular observation that we are interested in. So model 1 tells us there is 80% that it's going to be a 1, right? So this person is going to default in the payment in the first 4 months. Model 2 says 40%, model 3 says 60%. Basically what we do is we take an average. Very, very simple, yet very potent. Again, hello statistics. So it gives us 0.6%, and then we feel that we kind of accounted for all the peculiarities and all the inherent strength and weaknesses different logits could have gotten in the training from the data they got. And this gives us a result that we are a little bit more confident in. Binary prediction here, again, is basically like a majority vote, right? So again, with the averaging, you're just going to end up with a +1. So let's say, yes, this person will default, depending what your output is, right? So far, we've been mostly working, I feel, with probabilities of 1s or 0s, but you can also just train your model to produce you a certain output right away. The confidence intervals, just a different story. We haven't dealt with this that much, so I'm not going to be putting too much attention on it. Let's actually go through the kind of code example, and I feel it might be clarifying exact procedure flow a little bit better. So hopefully this sort of pictures are already feeling homey and cozy for you because you spend so much time in our studio. So we're going to be using the library air part, right? I really like this set of slides because it's basically going to be showing you how exactly we follow each step from data to the actual Y ensemble, right? To the actual decision, to the actual prediction. So we start here with data. We're going to be taking a very famous data set. This is, I think, who's going to be accepted to the university or not. So it's kind of binary. I think provided by UCLA, yeah. So this data set makes use, it has the ranking of the university, of the school this person is coming from. And then it has our target variable, which is admit, it's 1 or 0, right? We're converting both into the factor variables. We're going to be interested if the person with a certain GPA, with a certain ranking of their school is going to be admitted to a certain university or not. we're going to perform the data partitioning, right, at the bottom over there. Hopefully, again, something you're already fairly familiar with. Basically, we're creating an indexer, right, an IDX, a certain like a filter that we're going to apply on our data. And the information that is contained in this filter is that, okay, we actually want 70% of the data randomly sampled from the data set, right, without replacement in this sense, in this case. So in case I picked up one observation, I would not be able to pick it up again, right? So before, we were looking, okay, with replacement, right? I'm looking at the ball, I'm putting it back, there is a chance I will pick it again. Exactly correct, thank you. In case there is no replacement, then I'm putting it on the side, and then I'm never gonna see it again. And I keep sampling, and it's gonna be something new every time. Then I'm gonna use this indexer to subset, right, from the uni data set in order to get my training and my test data. 70% of data are going to go into training, 30% of data is going to go into test. I should invest time into explaining what floor is. Basically, there is a chance that you cannot subset exact 70% of data given the size of your data set. So floor means basically rounded up, right? Give me something that is the closest. Now moving on to modeling. First, what we want to do, and we're actually going to be doing something very, very similar in today's tutorial. First, we want to create the data frame that will contain the results for us, right? The predictions of all our models. If we don't create a data set like this, they're going to predict it and forget about it. You'll never be able to retrieve it from anywhere in our studio. So we're creating the tree forecasts data frame. It basically says, okay, have this number of rows that equals to the number of observations in a test set. Oh yeah, I skipped one, sorry. We decided we're gonna build 10 sets, right? We're gonna have 10 models. Every model supposedly should have a different data set for it to work. So we're setting our big T to 10. We're creating, as it's called here, reserve memory for ensemble members, right? This is basically going to be the list of our models. And then we're creating a little loop that says, okay, first of all, create BTS, which is take this sample from our training data. And on this sample, on this BTS, we're going to build our error part model, right? So here, the BTS is basically another sub-index that's going to be applied on our training data. So we're not going to build every model on the same training data that we got. We're going to build every model on the subset of the training data, right? To make sure that it's diversifying, that every model is seeing a different set of data. And then we're going to create and train a model, a part model, a tree, on this subsetted training sample, right, with the same target variable. And then the models that we got are going to get stored in this list that we called a tree bagger. Hopefully, again, it's not news for you. In our studio, you can see that the model is actually an object that is created, and you can see and you can access it in your environment after training. Okay, now we're going to forecasts. So the tree forecast is going to be the actual predictions that we can acquire after we feed in our test data into the every tree that we built. So we're saying, okay, pull in this loop from 1 to t, right? From 1 to 10, we have 10 models. For every model, do a prediction on the test set, right? Same test set, there is no difference here. And then this little guy here is making sure we're taking actually only one column of probabilities, because the prediction very often gives us two columns, the probability that it's a 0 and the probability that it's a 1. We usually want to extract the column with the probability that a certain observation is 1. And then we're going to store it in our tree forecast, and you can see that I here is indexing a certain column, right? So what our tree forecast is going to look like, it's going to be many columns, well, 10 columns, each containing a probability for the same observations, which is our row, but a prediction given by different models, right? This is exactly what we've just seen in this slide. So like here, we're going to get probabilities, but we're going to get 10 models, right? So we've done our predictions, and now we have the green bit over there. we're going to create basically another column or another variable that is just going to average by row. It's going to take all the probabilities predicted by 10 models, and it's just going to find an average for every observation. And this is going to be our y hat. This is our prediction. We arrived at the destination, right? Again, train set, taking samples from the train set. On those subsamples, we're training a model. We train 10 models. We ask those 10 models to give us their opinions on the same test set, and then we averaged over all those opinions, and we acquired our ensemble prediction. Right. Meta-parameter tuning and bagging. We actually kind of mentioned that in the process. There's a whole bunch of serious decisions you need to make as data scientists that is going to affect your results a lot, right? Going to affect how well you're performing, how robust your model is. So first of all, you need to decide which model you're choosing, right? We took our part now. Before we were considering logits. There is a whole bunch of other models you could be using. So you need to decide, okay, shall I build 10 logits? Shall I build 10 R-parts? Shall I build 10 random forests? And then maybe you would also, for bagging, it's usually homogeneous. So you're not saying, okay, I'm going to build 5 random forests and 5 logits, and then I'm going to combine them. You could also do that. I think bagging is usually kind of expecting you to do the same type, but you could. You need to decide on the number, right? Our T was 10. You could go for 100, 200. Depends on the size of your data. At some point, it might not make sense to keep on sampling because your sample size is going to get so small, right? But then again, what's a good sample size? Is it better to go for 100 Ts and then have 10 observations each? Or is it better to go to 10 Ts and then, I don't know, 1,000 observations each? Trade-offs. We're going to look a little bit at how exactly you can have a certain rule of thumb to make the decision. Yeah, here you have the practical advice, which is have more experts, right? Maybe they're going to have fewer data to deal with, but they're going to, really provide you with such a diversity of opinions that you can be much safer deriving a certain judgment from their opinions. So yeah, largest ensemble possible. Fantastic. Just get more data, basically. Here we're actually going to take a little, we're going to make a little experiment and see how exactly this whole numbering works, right? Size of sample, how many times we go over it, and etc. So we have a little hypothesis here that bagging reduces the classification error of a tree, rare part model, more than it reduces the error of a logit model. So basically it means that decision trees, as per our hypothesis, are more sensitive towards data training, meaning that logit maybe can catch up those ideas about your data better in fewer rounds than the decision tree. That in decision tree, in case it gets a little bit unlucky with the data it has in the training set, it kind of already fails to grasp what is going on. So you need to kind of do more samples, more models for trees than for logits. Let's see if it's indeed so. We have the same university admission data, and we have some results here. So for example, we have 100 iterations. Iterations mean that we, for example, had 1,000 observations, and then we took, I don't know, 10 samples over it randomly. Yeah, 100 observations each. And then I said, you know what? I mean, my sampling was random, and maybe if I now do this sampling again, I'm going to get different 10 sets. And then I'm going to get another different 10 models, and maybe it's even better, right? Because I don't have that much data. So you could run over the same observations again and again, because if you pick it by random, you're going to end up with a different 10 samples every time. Mixing and matching is going to be happening there. So for example, here, we've gone through our entire data set 100 times, and we measured the classification error for a tree and for a logit. And you can see, for example, that with logit, with the number of iterations, right, we've done it again and again and again, it actually kind of jumped a little bit at first, but then it converged in the sense of that you don't have an improvement or deterioration of your results at all. While the trees actually seem to be going all over the place, meaning that you can also get luckier or unluckier with the way you're sampling, right? the first 10 subsamples that you got might have been pretty good, pretty bad in our case, right? You have a very high classification error. But then we went back and took another 10 samples from the same data, just randomness gave us different sets. And then suddenly, actually, it was easier for the tree to derive a judgment, right? On the test set, it actually showed you better results. So you can see that it was going kind of up and down, up and down. How about we actually say not 100 iterations seem to be working. Indeed, tree seems to be more sensitive. So how about we do it 500 times? It will also converge at some point. At some point, you're basically, the difference between the samples is going to get so small that you're basically going to end up with the same models at some point. Because the model that had out of 100, 2 different observations, and then another model that had 2 others, there's not going to be much difference in their predictive performance. So at some point, it does converge, but then again, it's going to be your choice. How many iterations you want to try it for. At which point you want to stop and say, okay, I'm happy with where I am, no more iterations. Again, you can see that how vulnerable it is, right? Now, when you're doing a Kaggle competition, it doesn't make sense. If your model is going to be predicting cancer patients, I'm pretty sure the company that hired you would make sure to give you enough capacities to, so that you have whatever the hell amount of iterations you need in order to produce the best model. So it's really about the purpose, right? Indeed, you actually have to make, and it's another judgment call of yours. Where do I stop? How much is already too much? Am I happy with this? How many iterations I want to go for? What is the score that I really, really need to get versus the computational time it's going to take me? And then again, as students, we have alternative costs, they have other stuff to do. Your computer should be used for other things. It crashes, it burns, our studio, a board, all the pleasures of life. It's your decision. If you're seeing that, for example, that's why, for example, this sort of plots are so helpful. If you're seeing that for the number of iterations, you're already getting a flat line, you might stop. This question is going to be super duper current and important, for example, in next semester when you're going to start training neural networks. Because until it's done and you see how exactly it's going, you can say, okay, anything happening there, or am I just wasting my computational time? That is why it's so important to actually, at some point stop and give it a look. So what's happening inside? Am I getting any better? Maybe, I'm getting this marginal extra 0.001 less error, but then it takes me 3 hours and I have to submit in an hour. Well, yeah, choices. And you will develop some sort of an intuition there, and depending on the situation for your task, it will differ. Whenever we're talking about the actual world implementation and deployment, usually one dedicates significant resources to it. So it's a different story in comparison to the assignment for sure. But this is exactly why we're jumping around and screaming, please start early, because this is exactly what's happening, right? You don't know how many runs, you don't know how many takes you're going to have to go for in order to get a proper model. Maybe you need to try so many different variants that it's going to take you days as opposed to 1 hour. That's why you need to allocate enough time, because you don't want to see that finally the model is working, it's improving, oh my God, I'm getting the best performance, but I don't have enough time for enough iteration anymore. You don't want to be stuck in that position. Now, favorite topic. Biasvariance trade-off. I prefer this one. I want to talk about it. I think you probably have seen it before. The Biasvariance trade-off. So I feel it because both names are kind of statistical, and it's not what we call it when we're, on a daily basis training our models. It gets confusing. But this, I feel, is one of the biggest challenges, one of the biggest dichotomies that exists in the entire universe of machine learning, right? Like everything else is just parameter tuning in comparison to that. The point is, you can dedicate a lot of time, a lot of computational power, and then get super accurate prediction on your training model. And then it's going to be absolutely awful on your test set. Why? Because it learned exact way to explain the data that it's seen and failed to generalize. If you for a second think about computer vision, and the famous examples of looking at the pictures and predicting pictures, in case, I don't know, let's say cats and dogs. It may be that the computer learned that the cat always has, I don't know, something green on the side. It just so it happened that in your training sample, most of the cat pictures had like a little bit green on the bottom right corner. And the computer learned that this bottom green thing is super important, so whenever there is a bottom green thing, it's a cat. And it failed to pick up the fact that actually what we wanted to look at is pointy ears, certain shape of nose, maybe type of whiskers, and things like this. So there is a very high chance that in your data, there was some noise that the computer really tried to explain to itself, and it starts looking at this noise, just something like, I don't know, the person lives in that area and not in that area, but maybe that's just in the border, but the computer decided that there's crucial information, and because you trained it for so long and you pushed it for so long, it now thinks that this noise is actually a big chunk of this explanatory power it now owns. And next time you loaded the data from a different city, for example, right, it will actually fail entirely because it will start looking for this noise and will not find it, or it will find it in some other shape, and it will give you an entirely different set of predictions because it didn't learn how to generalize, right? So when we're talking about the trade-off between low variance and, about variance and basis, what we actually want, of course, is our model to be in the top left corner. We want it to give us correct predictions. This is a 1, this is a 0. And we want these predictions to be kind of nicely grouped in the sense of that the model will not have too much of a difference in opinion about it. What we definitely don't want is the high variance and high bias. So you can see that it's kind of sparse. The predictions are sparse. The model is not entirely sure where to place a certain dot, and then they're very far from the center. Both these cases are actually fairly hard to attain if you're doing things right. You want to be in the top left. Very often, if you're not doing things right, you end up with the bottom right. But more often, you actually have to run between the other two, between low variance, high bias, or high variance and low bias. So why sometimes low bias and high variance can be fine? This is exactly what happens in overfitting, right? Our model learned to predict fairly accurately, right? It knows where every bit is, but actually if it didn't learn to generalize. If we feed new data to it, it will be all over the place. Maybe the model did not overfit, actually it underfit. Actually you didn't train your model well enough, so it will be very, very sure about where to place all the observations, but it's going to be very far from the truth. This is definitely the most favorite of mine. So if we now take it into the whole plane of, trying to fit a certain curve, right, the model being a curve, around the data, underfitting, right, very high bias, but very low variance, would mean that you're oversimplifying things. And that your model did not learn that much from data. It kind of generalized, but it will be fairly weak. So the bias here means basically the error, right? How close you are to the true label. So here you can see that the straight line is very bad to actually grasp this kind of curvature of your data, right? It doesn't really give you a good idea what's a 1, what's a 0. Now, what we definitely do not want, because from here, we'll talk what are the remedies here. What is the usual case, right? Now we have the potent models, now we have the computational power. Actually, very, very seldom we face underfitting, right? Then you just have to be super lazy, run it once for 3 seconds, and then say, okay, here's my model. More often, we're facing overfitting. So you can imagine that the bottom right picture, right, our model learned to build a very, very complex curve around those observations, and we basically now have this perfect fit of the line. Our error is very, very low. Maybe our accuracy is 99% because our line is just fitting all the observations we got it very tightly. So we might be happy. The problem is, if you imagine us taking a test set, which will probably have kind of a different map between the blues and the reds, this particular super specific curve is not going to cut it anymore. Right? The model will actually, as soon as it sees something teeny tiny different, that's it, it breaks. It's like if you're learning another language and you learned, okay, here's my dialogue, 3 sentences, and then suddenly someone replaces one word and asks you something, you're entirely lost. Because you didn't learn the words, so you didn't learn how to combine them nicely, you just memorize a fixed sentence. You can no longer generalize, you can no longer, adapt towards the change of the dialogue, and that's exactly what's happening to the model. Now, what do we do with underfitting? We definitely want a better model, maybe with increased complexities. For air part, you might grow a bigger tree, for example, right? Or you want to maybe use something that is a little bit better than air part, which is random forest. For example, we're going to talk about it as our next slides. You want to maybe see, okay, I have 3 features. Maybe these 3 features are not explaining my data very nicely. Is there any way for me to get more features? Maybe I can create certain features. If you remember the tutorials in data cleaning, where we're actually doing a little bit of a feature engineering there. So basically, we're trying to help our model more. And then, of course, again, train longer. So in case you see that you're not getting a good accuracy, right? If your performance is really, really low, you might consider training more and then seeing if it improves you. But to be honest with you, longer training should be your 3rd step. Before you invest, this is just by experience, before you invest computational time into some model, make sure that you've reinforced your model as much as you could, that you gave it proper data, proper features, that you selected a nice model, and only then you can leave it running for longer and expect a good result. If you just create something of a very bad setting and you just run it for 3 hours, it's not going to get better. Or maybe a little bit, but that's inefficient use of resources. What do we do with overfitting? Perform regularization, and that's going to be the topic of the tutorial. Very nice. Or get more data. By more data, we actually mean different data. So you want to make sure that, for example, you're doing this bootstrap sampling, right? Make sure that your model is looking at the entirety of data, that it doesn't have this fixed data set that's never going to repeat in real life again, that's not going to appear in test set or anything. So you want to make sure that your data is as diverse as possible and that your model is seeing different bits of model and learning to generalize across those bits. So bias-variance trade-off is about underfitting versus overfitting. Very important. If it's the one thing you learned today, or at least revised today, let it be that. Because again, it seems to be an issue that follows students and professionals if you don't get it right in the beginning throughout like the entire life in the university and then at work, right? Do not underestimate overfitting. It seems to be kind of a boring statistical thing, but this is exactly, I mean, things don't crash and burn because your accuracy wasn't high enough. Things crash and burn and companies lose money and you lose job because your model was not robust enough. It's very important. So just going back to the whole ensemble, why ensembles are so good at actually handling the bias-variance trade-off is you can actually see how the complex and simple classifiers can be concocted. So for example, complex classifiers, right? Deep neural networks might have very low bias, right? They learn to fit this curve very, very close. They get you very good accuracy, and then they never generalized, right? Because they learned this exact line. The simple classifiers, right? Something very, very basic model that's not very potent, it might not give you a very high accuracy, but it will actually be general enough to be consistent with this accuracy, even if it's not the highest, throughout the training and then test set and then whatever new data is coming. So you want basically to combine things from both worlds, ideally. Actually, if you, to my knowledge, this is exactly how weather forecasts are made. So usually the meteo stations, they have several predictors, several models. They produce an output, they concoct them in a certain way because, for example, you have more trust in one expert than another, then you basically take the weighted prediction, right? We're going to say, okay, a little bit more sure about this one, and then you combine it, and then you have your forecast. I've been told that this is how weather forecasts are made. Just to wrap up the whole idea of bagging and why we kind of really like this as a method, right? Increases accuracy through reducing variance. So it basically hopes you, accuracy is basically bias. Higher predictive accuracy means lower bias. So it's basically trying to keep your bias fairly low, your accuracy high, by meanwhile reducing variance, right? When you're concocting different models that also different data, you're trying to make sure that you're not overfitting. So it's kind of helping you to solve the issue. Models don't get like stronger or weaker, but when you combine them, you actually end up getting a nicer one. So basically, if you think about the setting, you have a certain bias, right? And then you have a certain variance. By reducing the variance, you're basically ending up with a better mix. Most of the time, the bias is actually decreased. So actually, building on the idea of bagging, right? And this whole thing, okay, let's take different subsamples, we're going to bootstrap them, build different models, and average on all of them. Fantastic. We're going to have lower bias or same bias, but lower variance, which is absolutely awesome. Can we still do something else? And then, you know, whenever data scientists or statisticians are trying to make things more interesting, it always means that they're going to introduce more randomness into the procedure. Exactly what's happening with the random forest. So forest being a bunch of trees, here it's kind of fairly straightforward. Again, it's the same guy, Bryman, in 2001, introduced the algorithm. The key point here would be in the base model development. So you can think about it as we're building a bunch of air parts, but we're going to be doing it in a slightly different way. So it doesn't have to be trees for random forest, but almost always these are trees, right? Like a bunch of air parts. So we're going to be going, so base model development bit. We're going to grow each tree from a bootstrap sample of the training data, right? This is how bagging looks like. We're at the same level. But now things are going to get a little bit more complex, and this is where we're introducing more randomness. So while growing every tree, we will basically handicap it even more. We will not give every tree same set of variables. Instead, we will say, you know what? Not only this, it's going to be basically a random bootstrap sample of the data, also the set of features you can use as a model is going to be different. So we're only going to give you, out of 10 features, 3 random features, and then we're going to see how well you can do with your prediction. So not only the data gets to be randomized, but also the features get to be randomized, right? Our variables. So instead of using all attributes for every split in the tree, every split is going to basically get a new random sample of variables, not of observations, but of variables. So random sample of attributes. I don't know why we're naming it every time. Attributes meaning features or variables. Yeah. So basically, we're going to get a lot of different models, and not only these models are working with different data, but these models are also working with different features from our data set. So basically, not only randomizing on the row level, but also at the column level. After that, we take all our trees that we grew, we're using different features and different data, and again, we're doing the averaging, right? So we basically just ended one but massive component in the process of growing a tree. There is an important part here, though. If you remember, have we already plotted trees? I don't remember. There is actually a way to overfit using a tree very easily, even with a certain number of features, right? You can always basically find a way to grow the tree to every single component. So at the very bottom of your tree, you'll have not really bagged observations, like, okay, following this 1, 2, 3 rules, this is our 10% of our data set, 20%, 30%, whatever. But actually, at the very end, you're going to have each individual. So for every individual, for every observation, the tree can find you this perfect splitting rule, okay, turning at the age of, I don't know, the age should be below 16, the place of living should be this, and then basically the whole string only explains one person. This is overfitting, because if the tree can explain this particular, I don't know, 100 people perfectly, whenever we're giving them new people, probably going to crash and burn. Probably it's not going to, these people are going to be a little bit different, and this is where the tree is going to break. Now, as stated here, Bryman says we should not be pruning the trees. Pruning means we don't let the tree grow to the very bottom. We don't let the tree predict every person, like every single person at the end. We basically stop it at a certain number of splits, and we have our population basically binned in different categories by only using a bunch of rules. Usually we try to prune our trees. We're actually going to do that at the tutorial. We're going to see exactly how it looks like. But then again, it's your decision how much you grow the tree, right? Because as said here, fully grown trees have zero bias, right? It predicts every person perfectly, but then it doesn't really generalize, meaning it has very high variance that we of course can control via bootstrapping, right? Every tree is going to get a new sample of data. Now, random forest actually does a better job here because of those different features they're seeing, right? So even if we grow it quite a lot, because every tree will work with different features, and then we combine them all together, we can hope that they haven't overfitted altogether that much, right? So many handicapped trees, when combined, gives us a fairly robust, fairly well generalized prediction. I just added a little picture to show you how exactly it might look like. So we're growing n number of trees, and then each tree will try to classify each observation in a certain way. And the architecture of every tree will be fairly different, right? Depending on the sample set it's being built on, depending on the features it's using for every split, it's going to be fairly different trees. And then again, we're taking probability for every observation and we're averaging it. As mentioned here, random forest can be even more computationally costly here because of this extra randomness, because of those extra variants that are coming in. On average, a good performing random forest needs at least 1,000 trees, I would say. Depends on your data set, of course, and a bunch of other parameters, but it can take time. So be very cautious if you decide that random forest is your winning model, and it's fairly potent, even though it kind of sounds not too hard. It's actually a very strong, very good model that also yields a lot of explanatory power to you. So again, whenever you're going for the actual job in the industry, etc., I see a lot of cases when you build a wonderful neural network and it gives you a very high accuracy, but then it's a black box. You don't really know what happens inside. While random forest, you can basically plot it and tell exactly which features seem to be the decision-making points for the tree to do a certain classification, and that provides much more business insight, right? So very often you have to opt out for a model like a random forest because it provides you so much more explanatory power on what's happening inside, how exactly it's making decision, how exactly it's doing its predictions. So here we actually have question on the strategy. So let's imagine we can make fewer trees, right? Or we can make many trees, but every tree is going to work on a smaller bit of the data set, right? So let's say 5 trees, and every tree has 500 observations to figure out. Or we have, I don't know, 50 trees. I can do the calculation fast enough. It has a smaller data set to make its decision on. Here we basically, in order to answer that question, we have to consider yet another trade-off, unfortunately, which would be the strength diversity trade-off. If the tree has a lot of data to be trained on, it's stronger, right? It's seen more options. Your expert has much more data to derive its conclusion from. However, maybe you have a lot of experts, and then they only know their bit of the forest, right? They only know something about the 10 square meters around them. What is better? These experts that only know 10 square meters around them might not know very well what's happening in the outer world, but they're going to have very, very different opinions, right? The person who is an insider in the company, the person who is a market broker, the person who is a hedge fund manager, they might not know very well what's happening in the areas of other experts, but this is very good because you're going to get a higher diversity. They might not be super right, but you will at least have a big pool of opinions to choose from and to average over. This is our strength versus diversity trade-off. So in case we're going for, okay, I don't want to do the karaoke here really, you could read that. It's actually a big research field, and people have been trying, again, to find some sort of a golden needle there. Here, like to bring you slowly to the answer, we actually need, like, why diversity is so important is because when we don't have enough diversity, when everybody answered here, yes, the stock is going to go up, we might end up with basically equally wrong predictors, right? They might be equally right, but they might as well be equally wrong. You have nobody in the room raising their voice saying, maybe this is not the best way. When you basically have a bunch of yes men, could be right, could be very wrong, right? You're not hedging yourself against the possibility that maybe they don't know what they're talking about. Just a little example for you what it can look like. So here, for example, we have a bunch of regressions that kind of all derive, like they all are very similar lines. So none of them actually captures better or captures worse. And when we average among them, we don't really get a better result, right? They are okay, but there's no way for us to capture this little extra. And that little extra could have come from the model that is maybe, I don't know, getting this red square to the left side and right dot to the right side. Maybe if this model was there in the mix, we would get slightly closer to the truth. That's why diversity is so important. So just to skip ahead a little bit, better to use larger forest, right? More trees. There might be kind of more wrong, but given the fact that they're going to be trained on this like different data and you're going to have more voices, you will actually end up with a better result rather than if you had 3 trees that would probably could end up being not as diverse in their opinions, in their prediction as many forests. Although to be honest with you, before the class, I actually asked several colleagues of mine, like, yeah, can you answer this question? And I did get different answers. So intuitively, you could actually go either way. It's like, yeah, but why would I need a bunch of super weak models? They're probably all like wrong. The answer is depends. So sometimes it makes sense to try both and then see what brings you closer. Again, there's like a little explanation why exactly the trees are very good for random forest. Again, I've never seen random forest used on anything else but trees, to be honest with you. I'm not entirely sure how much time I should dedicate to that. But the point here is that because of this extra randomness that comes from sampling from different features, you increase diversity, right? So, and this is what we want. So this kind of brings you even closer to the nice result. Right. This is an important bit, and we will actually cover it additionally in the tutorial. There is a certain number of parameters. I actually think there are around 4 meta parameters inside the algorithm that can really make a very big change to the performance of your random forest. So yes, we can like choose which models exactly are going to be grown, which models exactly are going to constitute our forest. Let's say that it's trees, although you could go that, for example, for a neural network, possible. Again, as said, just like in bagging, we can decide on the bootstrap samples, right? How many iterations, etc. As Professor Lessman is pointing out here, size of the bootstrap sample is often overlooked. And this is actually where I would like to draw your attention to this, in particular when it comes, for example, for home credit data. Whenever you're having a highly imbalanced data set, which we basically have with the home credit data, the size of your Bootstrap sample is of big importance. Because in case it's too small and you're not performing any extra effort to make sure that your clients of interest, right, your dangerous clients are in the sample, you might end up with a model that's never seen anybody that defaulted. You can imagine that this model might not be very potent when it comes to actual defaultees in the test set. So you either want to make sure that it's kind of fairly big so that you have enough representation of your class of interest, or you can also take a certain type of a stratified sample when you're ensuring that it's the same balance of ones and zeros in every subsample. So bear that in mind. Now, the extra randomness is going to be reflected in the mtry parameter, and this one can also make a very big difference. This is basically from how many features does your forest have to randomly sample at every split. Does it have 3 features to choose from? Does it have 20 features to choose from? You can imagine it can be quite a difference. Although there is a good rule of thumb there, which is your mtry should be the square root of your overall features. So in case you have 100 features, in our case of the home trading data, I think we have 86. So you might want to go for the square root of that. So right, we would be going for maybe 9 to 10 features for our mtry. Right, this is random forest, right? We started with bagging, which introduced a certain number of randomness and this group of experts whose opinion is further on averaged. Then we kind of saw the way to improve this by introducing another level of randomness, which are features. We then considered what is our trade-off. Do we build a stronger model? Do we get more models? How is the whole variance trade-off thing, variance bias trade-off thing is working for us? We hopefully learned it's very important. Keep that in mind. Familiarize yourself with the random forest. This is very often the go-to model. And this is very often your benchmark. Not really logit. Logit is nice, for example, for the binary classification, but random forest is almost always something that is necessary to show. So in case your model, whatever you came up with, can outperform random forest, logit is a given. It has to outperform logit at least. Then you're kind of doing fine. Then your model is credible. So we wanted to introduce a little bit of ensemble learning theory just because it's a whole area of research, and maybe some of you will find it interesting for further exploration and consideration. After you build your models, after you got your result, after you averaged, after you got your predictions, the time comes for the model evaluation, for the assessment of your results. And this is exactly what ensemble learning theory is dealing with, right? When you decided, okay, I'm going to throw 30 random forests in 5 logits and then, I don't know, a couple of neural networks on top, concocting it all, there we go. How do you evaluate that? How do you compare models in between themselves? Given the fact that the models are becoming such weird beasts, you need a couple of extra tools at hand for that. So obviously your model can be coming up with different outputs, right? Some models output probabilities, some models output binary predictors or even confidence intervals if you want. You need to be able to compare these models nicely. As we learned, diversity is very important. However, however, it's not necessarily a good objective to create ensembles. And this is where your measurements are coming in. So for example, one of the ways to actually look at the diversity of your model and then see where it's standing is to use some of the diversity measures. So there can be pairwise, right? So you can be comparing one model to another. It can be, for example, entropy, when you're just comparing all the models with all the models, not really pairwise. However, as shown here, this cross table, for example, for the discrete class prediction, is like a very often go-to in case you want to show these models. So how many correct predictions does this model give? How many? You basically see the level of disagreement, right, or agreement between the models. This is how you evaluate the diversity. You can go pretty complex. with your measurements, right? There's yield skew coefficient. It basically, you can see that they try to concoct these different bits of disagreement in different ways in the attempt to produce the most, I don't know, meaningful metric for you to derive your choice from. So I guess it's not really for your competition, but in case you would be to write a paper, or in case you would be to submit something a little bit more scientific, and then you have several ensembles, this would be a very important bit, right? You would want to show what exactly is happening, how exactly the choir of your model is sounding like. Are they disagreeing? Are they agreeing? Maybe if it's a multi-class, on which classes they're like very unanimous, on which classes they disagree. If it's probabilities, then to which extent they actually differ from each other. That would be an important bit. Of course, doing a little visualization is kind of always a nice idea. Here you can just see that you have on y-axis what is the percentage that was correctly classified, and then you have on x-axis the correlation between the two models. Correlation can be coming from here. Yeah. This is just another way. So basically, every dot here is the pairwise comparison of models, which is also another way to go. We can go even further on. I don't think I would be dedicating that much attention to it. However, in case you ever see that in the paper, I would like you to know what it is. Ensemble margin is another way of evaluating the combination of different predictors. What kicks in here is the weighting, right? As said, you might not trust your experts equally. You might say that, okay, actually, you know, his opinion weights, I don't know, as 0.8 for me, or her opinion weights as 0.95, and her opinion weights as 0.3, and then you acquire your prediction, right? So here we basically just have a certain weighted sum of a certain oracle output. Oracle output here being classified correctly or incorrectly. This is a little example. I find this one a little bit confusing, but the takeaway here is the research showed that the higher the margin of a certain ensemble, the better performance it usually gives you. So, for example, in the bottom line, we have this very high margin that is calculated using this formula, right? And you can see that there is a certain unanimity and it's fairly accurate, right? So all predictors are getting very accurate predictions, are giving it very accurate opinions. So it shows a high margin. However, for example, here on the line 2, I was talking about the bottom line. On the line before that, right, slightly different story, you actually have base model predictions that are weighted equally, but then you have only one guy predicting it as, for example, 1 and not a 0, and it gives you a fairly low margin, which is supposedly not good. This is just some theoretical things in case you ever go into the whole ensemble modeling, evaluation and comparison, development of your own concoctions, and etc. Very quick summary. We kind of, I think I already recapped it, right? We talked about bagging, we talked about random forest, we talked about Biasvariance tradeoff. I would really, really motivate you to try out random forest. This is going to give you a first kick for your competition prediction or for whatever modeling you're doing, definitely. And then as a second step, do experiment with ensemble learning, try putting together linear models with non-linear models, weak models with strong models. And it's almost always, you know, like diversity flourishes, it almost always gives you an even better result. So this, supposedly, after this lecture, you should be able to really boost your results very, very nicely. Hopefully you're already all experimenting with that, so it will be something to build up further on. As a next lecture, you will be talking about the boosting algorithm that is supposedly even more potent than bagging. The model called XGBoost has been a very big winner in all the Kaggle competitions. I think huge, those that are not done with text or deep learning, etc. Almost always when you see the winner, they ended up with the XGBoost model, extremely potent, extremely powerful. And you're going to be talking about heterogeneous ensemble learners, meaning you have different models in the mix, right? Not just a bunch of trees, not just a bunch of logits, but when you actually saying, okay, this model is capturing linearity very nice, but I'm expecting certain nonlinear dependencies there, so I'm going to marry them together and see what comes out. That's pretty much it. On the tutorial, we're going to be talking about regularization, which is going, again, in line with the whole Biasvariance trade-off. Very important bit. We're also going to build some more pruned and non-pruned error parts, and we're going to see how forcing models to generalize can give us better results than just going for full data, full number of parameters, and the full building. Thank you very much.